over there, and I work on llamas. Right now, I'm leading the Llama4 pre-training team. Prior to that, I was leading Llama2 and Llama3 teams, and before all of this Gen AI revolution started, I was working on machine translation and speech. So quite a bit of a journey. I'm a researcher and engineer at heart, and I don't particularly use those models, so I know a lot of people in this room probably have way more experience than I have in using these models. I only train them, but so when I was thinking about what should I talk to this audience, I decided I'll share the story of building llamas and some challenges that we have, and invent how you can help build better llamas in the future. And tomorrow there will be another talk from Joe Spisak, who is actually a product director on our team, and he will be able to cover the real practical use cases of those models. So if you have questions about how to use those models, Joe would be the right guy to answer those. Wait, let me get started. So the evolution of Llama, it all started in February last year when we released Llama 1, which was an interesting release. Let me share why. So first of all, it was a research-only model. It was released with research-only license, meaning you cannot build commercial applications on top of that. And it was not even built to be an LLM, meaning the team that was building this model, their main goal was not necessarily building the state-of-the-art LLM. It was kind of a byproduct of the other project that we were doing. But we released it and it was great. People really liked it. Back when we released 4 model sizes, it was trained on 1.4 trillion tokens, which sounds very small these days. Back then it seemed pretty cool. And the context length of that model was just 2,000 tokens. Oh, and it was only pre-trained model, so like really bare bones. Pre-trained means you can't really talk to that model. It's only able to continue whatever sequence you input in it. So we released that model and it kind of exploded. So that's the picture from a paper published in April last year. So just 2 or 3 months down the road. And we put a nice footnote here, like, hey, due to a huge number of use cases of that model, we just cannot put them all in the same picture. So people took Llama, the original Llama, and they started using it for everything, for medical use cases, for legal use cases, for finance, for education. People did multimodal adaptations. They figured out how to feed images into those models. And of course, we did multilingual. So the number of use cases really exploded at that time. And then on our side, we were looking into those beautiful curves. So that's what we call training curves. We show training loss on the y-axis versus the number of tokens you train on the x-axis. And typically the lower is the better. So what we see when we look at those curves is like, hey, you make the model bigger and it gets better, and you train it for longer and it also kind of gets better. So those were the 2 very important axes of improvements that we immediately realized when we trained those 4 models and released them. And we started to think, hey, how can we get them even better? So the first follow was Llama2, which we released in July of the same year. And that model had some substantial changes. The most important one, it was commercially available. It was not research only. And what it practically meant when it happened is that we had to revisit the entire training data that we used to train this model. And we actually ended up with more training data. We trained it on 2 trillion tokens with 4,000 context length. And another most important thing is that we did not just release pre-trained model, we also released instruction fine-tuned model, meaning the model you can actually speak to and have a meaningful conversation with. But when we looked at those curves again, the curves I showed you before, but now for Llama 2, and they show exactly the same trend. They keep improving as you make the model bigger, and they keep improving as you keep training for longer, and there is no sign of saturation here. So it looks like you can just keep scaling and it's just going to work. We did make a lot of advancements in our training pipeline for those models for Llama 2. Like again, for Llama 1, it was just a pre-trained model. So whatever you see at the left bottom corner, that's pre-training. that's kind of the dumbest stage of the training of those models. The objective here is very simple. You just tell the model to predict the next token in the sequence, and you train it on that, and then you feed gobbles of data into that, and you need a lot of GPUs to do that, so it's really difficult engineering challenge, but the optimization objective is quite simple. However, again, the model that you get is not really a chat model, so to make it a chat model, you need to align or fine-tune it, and that's the next stage that is shown on this picture. And it's broken down into multiple sub-stages. You first need to feed a bunch of examples into the model of what you would expect it to answer if you ask it a question, and then you want to keep improving and iterating. Like basically you ask this model to generate a bunch of examples of answers, you ask humans to rate those answers, you use those ratings to improve your model, and you keep iterating this process. And that's where we found another scaling axis for those models. So on this chart we show our subsequent iterations of RLHF. This is our model alignment fine-tuning procedure. And the more iterations we do, the model just keeps getting better. So that was also quite exciting to see. And it's getting better across multiple dimensions. It's becoming more helpful, it's becoming more safe. So it just felt good to get there. So let's keep on here. This year we actually did another major release. We released Llama-4. It started in April. So in April we released 8B and 70B models. And then in July we released our flagship, the biggest model that we have for a 5B. And just a week ago we released our tiny baby llamas, 1B and 3B, that you can run on device. And we also released multimodal adapters for those models. So again, just a quick recap here. Same commercially available for practical applications. This time trained on 15 trillion tokens of data. That's an enormous amount of data that we have to collect to make it work. And we also expanded the context size of those models, making them useful for working with long documents. So again, I already talked about it. So 2 model sizes released in April, 8B, 7B, 70B, 128K context length. We added multilingual support for those models back this summer, and we improved the tool use for them as well. And 405B is definitely a model of a class of its own. It's very competitive. Let me get to that in the next slide. But it's pretty big, I'll be honest. Just running it on your laptop is probably not really an option. Just to get it running, and we released quantized version that make it easier to ship this model, but even with quantized version you need 8 H100 GPUs, which is a lot, just to run inference on this model. So we envision these models to be used for synthetic data generation, fine-tuning, and distillation for any practical use cases. And yes, it shows pretty good performance numbers. We measured it on a lot of benchmarks, like 150 benchmarks. They're all in our papers. And it's pretty competitive. Of course, it's better on some benchmarks, worse on other benchmarks. It's pretty competitive with other state-of-art LLMs, including closed source ones. And then, of course, we did human evals to make sure we are not just cheating on benchmarks. And it's also pretty competitive over there. It's pretty comparable with GPT-4. It's pretty comparable with Claude 3.5 Sonnet. It's a little bit behind compared to GPT-4. Now, the topic of this talk was like, hey, what does it even take to train those models? So, what does it take to train Llama? Well, as I mentioned, I work on pre-training, so that's kind of the most painful part for me and close to my heart. So I'll talk a little bit about pre-training. Well, conceptually, as I said, pre-training is very simple, right? You have a very simple objective, just, hey, model, go ahead and predict the next token in sequence. It's very, very simple. But if you look what is actually happening under the hood here, it's pretty complex. So the first paragraph here is a quote from our paper, and it basically describes how we do the initial stage of pre-training. And it's like, hey, yeah, start with this learning rate, do that number of steps, then increase learning rate, then a new learning rate, that number of steps. Oh, and by the way, you need to start with small batch size to make it stable, and then do bigger batch size so that you're efficient, all of that stuff. Yeah, the good thing is that we found that this recipe is stable. But like just figuring out how to get to that recipe, there is enormous amount of knowledge and experience that goes into that to figure that out. And that's not even everything. You will need to do way more to make those models good. Like some things that we did is we did data set adjustments as we were training this model. We figured out that it's much better to start pre-training with lower quality data and then backload higher quality data towards the end. That helps. We had a long context expansion stage. Again, for efficiency reason, when you start training those models, you normally want to start them with smaller context window. And when you want to expand it towards the end, that brings up a lot of new challenges with scaling all of this. And then the latest stage of pre-training is annealing, where you really want to squeeze the juices out of the model and push for performance. And here you're doing it with the highest quality data that you can possibly get. So, as simple as pre-training it is 4 stages of quite complicated adjustments that need to be done. Now, what challenges do you see when you train those monsters? And one thing that people don't talk about much is just pure infrastructural challenge. So for Llama 3, we trained them, actually for Llama 1 we trained on 2000 GPUs, that was relatively easy. Llama 2 was 4000 GPUs, it was okay. Llama 3 was trained on 16,000 GPUs, and when you run such a massive amount of GPUs together, things inevitably fail all the time. It's just hardware is hardware. So in our practical experience, we had 8 interruptions a day, meaning 8 times the whole thing kind of stopped and you have to restart it from a checkpoint. And in our paper, we do report the collection of errors that we encountered, and you can see that, hey, faulty GPUs was a pretty big issue. There were issues with GPU memories, there were software bugs, there were issues with CPUs and network switches. Pretty much everything that could possibly fail at that scale fails. And that's just the beginning. If you think about what Llama-4 is supposed to be, I'm not going to be able to tell how many GPUs we're planning to train on, but it's going to be bigger number than 16,000, and if we had so many failures back then, how many we're going to have? A lot of those failures are inevitable. So those are real practical challenges of scaling those models. The other interesting challenge that I haven't heard anyone talking about is just the emotional component of it. So when you get into this training run, you're like about to burn like hundreds of millions of dollars maybe. Right? And you pull the plug, you started. And before the training run, the biggest ablation that you ever had, or the biggest experiment that you ever had, might be like 10x smaller. So there's no way for you to know how good your run is going to be. So you started on the first day and you start watching some metrics. In this case, we watched MMLU, along with others, but like we observed MMLU closely. It's a quite popular metric. And initially, you see kind of a rocket ship. So the model performance starts improving very, very quickly. And in the first like 2 or 3 days, you see a dramatic spike in performance. You're excited, it looks great. Then it starts to flatten out very, very quickly. Like closer to like second week, you're like, okay, it's not improving that fast anymore. It's still climbing up, but it's like not really that fast. And another challenge here is that it becomes really noisy. So those metrics were not like super accurate. There is a lot of noise when you measure them. So what you observe on a day-to-day basis is like ups and downs all the time. And sometimes you don't see meaningful improvements for weeks of training. That is just training. And then like you need to go all the way many months down the road sometimes to see the ultimate performance results. And it's pretty much impossible to predict where you're going to be in the end. So just the emotional component and also this exercise is very, very hard to describe. And that's why you see researchers like looking like zombies sometimes when they train those models. Now you may ask, but hey, the scaling laws and everything, like can't we use scaling laws to predict how good they're going to be? Well, let me tell you the story about scaling laws. So these are like funny things. Again, the scale of experiments that you can practically run on a daily basis is on the left side of this graph. So this graph shows your like compute budget, how much flops you're gonna train on, or how many GPUs. and on the y-axis it's some metric of performance, doesn't matter which one. So the experiments you run when you play with the model, they are on the very left side. You might have been lucky if you trained previous Llama before, like in our case it was Llama-4, then you have some data point somewhere closer to the middle, that's still pretty far. And you were trying to predict what's going to be on the right-hand side on the graph. And by the way, nothing here is linear, so there's no way to draw a straight line, it just doesn't work. So predicting what's going to be the output performance is pretty much impossible. We did some, in our paper we published some scaling law experiment results, and we did some work towards getting better ways of predicting model performance. So instead of trying to predict it directly, we're measuring model perplexity and plotted model perplexity on our test sets, and we plotted against the compute budget, and that relationship is linear relationship on the left-hand side here. And then using that relationship, you can map it back to the model performance at your target metric in the end. But still, it's quite complicated exercise. It's not super reliable, but it gives us some sense of where we are heading. Now, I'm going to the next challenge that we're going to face, and for Llama-4 it's going to become even more important. So data. Again, we have established pretty robust scaling laws on the data side. We know that if you want to increase your compute budget and train your models on, let's say, 100x more GPUs or compute flops, that would require you to roughly 10x model size and roughly 10x data size. So if we train Llama-3 on 15 trillion tokens, then, and if you want to 10x that would require 150 trillion tokens of data, and there is no place in the world where you can download that. That just simply does not exist. So getting the training data is really big challenge, and we have some ideas how to solve it, but that one is a big one. So what we are trying to do to solve those challenges is we are trying to figure out how we can get more data efficient, like how can we train better models with smaller amount of data. We need to figure out how to scale synthetic data generation. Obviously, humans do not produce vastly bigger amounts of data on a day-to-day basis as fast as we need. So can our models produce that data? That's an interesting research problem, but nobody has really solved so far. And we are trying to figure out how we can use multimodal data. So let's move on a little bit to post-training. Again, the pre-training was relatively objective was simple, and the whole pipeline was relatively straightforward. Post-training is a whole new level of complexity on everything. Instead of just having one objective, you suddenly have multiple objectives here. You want your model to be good at math and good at reasoning and good in maybe law domain, legal domain, and whatnot. Some of those objectives are actually competing with each other, and it becomes really difficult to trade off between those. One example I used to give before is model helpfulness and model safety. They're pretty competing objective. Naturally, when you want to make model helpful, you want it to be able to answer any question. But there are some questions that you don't really want model to answer for safety reasons, right? And that becomes really hard to trade off between those two objectives. Anyway, so our post-training pipeline is quite complex. We use heavily synthetic data. We had to train multilingual and code experts to improve performance on those specific domains, and we use DPO instead of TPO that we use for Llama-4. Now, some of the challenges I already mentioned, but let me cover them a little bit more here. So for post-training, we really need high-quality data. So that example here is an example. The first one is an example of fine-tuning data that is used for Llama-2, and it is written by human. So write a poem to help me remember the first 10 elements of periodic table, given each element its own line. I don't know how about you, I cannot write such a poem, there is no way. So, and you need a lot of those examples for all sorts of domains, Like you need examples in quantum physics, you need examples in math, but not. It's very, very difficult to get high quality data, and the quality here really matters. So that one is a big challenge for post-training. We also need to carefully balance our objectives, which I already mentioned. We don't, like if our scaling laws in pre-training are not super mature, our scaling laws in post-training are like even less mature. So we don't know how much more post-training we need to do, how much data we need to feed into the model to achieve certain results. So that's another big challenge. And then finally, we sometimes don't even know how to measure model performance, like evaluation data sets. Let me go to them. The evaluation data sets is yet another challenge here. So first of all, the life cycle of many benchmarks is very, very short. From the time a benchmark comes up and people start using it and broadly adopting it, to the time it becomes saturated, it's usually just one model cycle. That's what we see. There are many reasons for that. Some of them are good, some of them are bad. Like there is obviously some training data pollution happening, either intentional or unintentional. There might be some cheating happening as well, with people like really willing to push hard to get good numbers. But either way, it is happening, and this is something we have to recognize. Some things are just really hard to measure, especially if you go into multimodal domain, if you move away from text. Like how do you measure the quality of generated images? There's no automatic metric for that, so you have to, like, a human has to look into that, and that does not scale. Same with speech. If you generate speech, then how do you measure the quality of that is really difficult. But even on the text side, how do you measure things like, hey, what is the tone of the model response? Like, is the model friendly? Is it chatty? Is it like too conservative? It's hard. And in general, I think we experience a shortage of really good benchmarks for all of those reasons. So I promised to ask you how can you help, or like throw in some suggestions into this room. So let me get to that. I think we definitely need better benchmarks, and I think community, like people who actually use those models, are best positioned to develop those benchmarks. Like pretty much everyone who has a specific practical use case where they use those models, I'm pretty sure you all have some test sets that you use to decide whether a new model is good or not, or how much better it is. So I think it would be very important at some point to get those benchmarks out. I would encourage you all to start releasing those. Obviously keep some amount of them private for obvious reasons, and because you don't want your benchmark to be leaked into the training data. So you want to keep some amount of them private, but please do release some public benchmarks that are relevant to you, that show model performance on your specific use case. That would be a win-win to everyone, because when we will be able to track performance against those benchmarks when we train those models, and when you can track a metric, you can improve on that, you will be getting better models in the end, because like, once we train them, then hopefully they'll release them, and you will get measures that are relevant for you. The other thing that I want to encourage community to do is to invest more into post-training. One thing that people don't quite maybe realize, that DPO, the technique that we use to post-train Llama-4, was not invented in a big industry lab. It was invented in Stanford, and they didn't have tens of thousands of GPUs to do that. So it's definitely possible to do significant improvements in smaller settings. I think we need scaling laws for post-training. We need to figure out how to make do post-training more efficiently, and this is something that can also be done at a smaller scale. And finally, we need better data. Again, I think a lot of people here fine-tuning the models and have those data sets. I understand the data is private for a reason it is private, but there may be other ways to make this data available for pre-training of those models. Like we can probably generate some proxy synthetic data or whatnot. We can figure it out. I do want to encourage the community to think about those things, because that will really help make us next versions of Llama much better. Thank you so much. If you want to learn more about Llama, llama.com, our new domain, please go there. It has a lot of recipes, code, notebooks, and everything else. And I have 4 minutes for questions. Thank you.
When you talk about all the training times and the cycles and everything, what percentage of that is hyperparameter tuning? Is that just in the pre-training?
You do a lot of parameter tuning in post-training as well. The post-training iteration cycle is much shorter, so you can do a lot more there, actually. Pre-training iteration cycle is really, really long and really, really expensive. So for pre-training, we do a lot of parameter tuning at much smaller scale, and that's why we built all of those scaling laws that allow us to actually tune those parameters at smaller scale and then extrapolate into a larger scale.
Thank you very much for his presentation. I do have a question about data pollution. So one is, do you have existing mechanism or techniques kind of like handle that right now? And another question is, since we talk about synthetic data, right? So I believe there could be data pollution around that as well. Is there any mechanism to handle the synthetic data pollution as well? So, thank you.
Yeah, we do use a lot of the techniques to kind of to reduce data pollution. Like you're looking for similar examples in training data and try to remove them. But in the end, it's not always possible. They're constructed based on Wikipedia. Now, what do you do about that? You don't remove Wikipedia from your training data. Really, it's like the most high quality source. So you can't really do that. But you do try to remove things that exactly match the benchmarks or very, very close to benchmarks. Those are the things we're definitely doing. On synthetic side, so far hasn't been an issue, but I think it really depends on what kind of techniques you're using for synthetic data generation. Like a lot of synthetic data generation right now is on code side, where you can actually generate code and compile and run it, validate, and that helps a lot.
Thank you, Sergey. Can you tell us what to expect in Llama-4?
So I have a tweet with this bigger and bigger monster. So we expect Llama-4 to be much bigger and much stronger model, but it's very, very difficult to give exact predictions on what kind of capabilities you should expect from that model, because some of them are emerging, right? They only show up at a certain scale, and so far no one really has achieved that scale. GPT-5 is not out, so we don't know what we're gonna find. I guess they'll find out as we train and learn.
So I have a question about training data. You mentioned multimodal and ideas on how to use that. Do you mean like audio data or video, or what kind of ideas do you guys have in mind?
Well, we have many ideas. The question is what we can execute on. We want to use everything, ideally, right? So in some perfect ideal world, you would want a model that can consume all sorts of data and train on it, no matter where it's, no matter what modality it is. It might be that some modalities are less informational dense as text, like text has a lot of information in it. Images may be less, I don't know about video, so that might be the challenge.
So I have a question. So the first model was trained on human data. So what happens when more generative data is put into the internet and you train this model on this? Is there like limitation or a corner to avoid this?
We don't know. I mean, in research we sometimes call it distillation, when you use synthetic data produced by a model to train another model. I guess it is happening right now on the web because there is so much synthetic data already there. But we don't know the impact of it. I've been working on machine translation before LLMs, and where it was already an issue, where a lot of data on the web was automatically translated already, so if you train on it. So I guess this is something we'll have to figure out as we learn, but it's gonna be a challenge for sure.
Okay, we'll take one more question, and then we're gonna transition speakers so that folks can catch Sergey in between space.
My question is, when do you think that Meta might pivot away from kind of training llama models? Do you think that they'll ever stop creating new models of the
That's a great question. So far, we are seeing that these models keep improving as we train them for longer on more compute and on more data. But there are obvious bottlenecks. Some walls what we are facing, like data is one wall. Scaling compute going forward is probably also going to be more and more challenging. So we'll see what's going to happen when we hit those walls. Maybe we'll start scaling in other dimensions. Like it's clearly that OpenAI is doing some inference compute scaling, so that's another interesting dimension to scale into. Who knows, there might be more. So will the next models are going to be more and more pre-trained? I don't know, but we'll keep improving as long as we can.
All right, let's give a round of applause. Thank you so much.